And a Class A amplifier amplifies 360 electrical degrees of an input signal. Now, of course, what we're dealing with in lab is we're dealing with a sine wave because it just makes it so much easier to calculate gain and that kind of stuff. If we actually looked at the output of a that's coming. Well, it would be hard to trigger. We can trigger it, but it's not going to make it much different because it's audio. Audio is constantly changing. So what we have is that we can see the bass and then all the trebles and the mid-range and everything. It's all composited together. If we put this on a speaker, it would be sound. And so this is what audio looks like. But it's just a combination of sine waves. That's all it is. So even now, if I was to look at my voice, I have different pitches, right? You understand that we go through, and we'd see it changing too. So this is audio, guys. This is what audio looks like. So this is what your amplifiers and stuff, audio amplifiers have to handle. Is that cool? So this is music. Voice wouldn't be as cool, but you can see the bass. So the bass is low frequency, and then everything else is riding on that. Looks like it's fixing to change songs on it. So, but what we do in our lab, of course, is we look at sine waves, because that way, what would be the gain of this amplifier? It'd be impossible for me to calculate to see if the gain was right, because this is what? It's all over the place, right? You understand? But it's just a combination of sine waves. So normally what we do when we troubleshoot an audio amplifier, we can look at this, and we can tell if something's there or not there, so we can go through a stage. But if I was trying to check the gain or the bandwidth of the amplifier, then I would use a function generator. What is the bandwidth? That's definitions, guys. What's the bandwidth? You hear that all the time, but if you don't understand what bandwidth is, what does that mean? All you know, bandwidth, the more bandwidth I have, the faster I can spin data. But what is bandwidth? So here you use the term all the time and you have no idea what it means. But it sounds cool, right? It's just like saying dB, 3 dB. You know what 3 dB? Oh, that sounds cool, but if you don't know what 3 dB means, it's nothing, right? So what is bandwidth? We talked about it in this class. Nobody in this class knows what bandwidth is. Well, it's not the media. What is media? How do we define media? Huh? No, media is not information. So this piece of wire, this is media. This is media right here. Is this information? It's what information flows through. So media is what information goes through. So if we say multimedia, it means we use different things. So I use visual, right, media. That's the media. I use sound, right? You understand? So that was the big time. Multimedia. It means instead of giving the information as text, you let it speak to you or something like that. So you can read it, not only read it, but what? But also hear it. So media is what information transfers through. Broadband is a type of the way we send information. So baseband and broadband are the way we send information. So broadband means, so I've got media. So let's say I got a wire. I got a conductor. And I don't know, wrong thing, Rich. So every media every media has a bandwidth. So technically, it's a little different on the internet. Technically, media is the range of frequencies a media can reliably pass. That's what bandwidth is. And every media has a certain bandwidth. So if I take a piece of wire and I might put DC on it, that's okay. When I start putting AC on that thing, things happen. It couples, it creates capacitive, it creates inductance. So sooner or later, the media itself is going to block the data that I'm trying to send at a certain high rate of speed. So every media has a bandwidth. Now, what we would do technically, if we looked at what we call a bandwidth curve, then what would happen is we come up here and we would have a bandwidth curve. Now, most electrical conductors, F1 would be 0 hertz because it passes DC really well. But if I was to look at a regular media, it would come up here and go off. It would start off. This is volts. This is frequency. And what would happen, a bandwidth curve will look like this. We would start off and the media would almost pass no information. And then it would come up and it would take off. And then it would hit the maximum and it would plateau. And sooner or later, it's going to hit the higher length and it comes up here. Right here, if we was measuring voltage, it would be 70.7%. This is what they call F1. This is what they call F2. And the bandwidth, the way we'd measure bandwidth, it would say F2 minus F1. And that would be the bandwidth. So that's bandwidth. Now, why 70.7% or minus 3 dB? We've talked about that in this class too. 0.707, we use that a lot. But why? Because bandwidth is the half power point, not the half voltage, it's the half power point. So that means if I was getting 100 watts right here, then the bandwidth would occur at 50 watts. But power is hard to measure. Voltage is real easy to measure. So we looked at that. So let's say I've got 10 amps. So power, 10 amps times 10 volts would give me 100 watts of power. Right? So what would be the half power? How many volts would give me half power? 50 watts. Okay, let's do it. So power, voltage and current are directly proportional to each other. So what that means is if I half the voltage, I half the current. So I go 5 times 5, and by George, that's 25 watts. Power varies with the square of the voltage. So if the voltage goes down 1/2, it's going to go down, the power is going to go down 1/4. If it goes up, it's with the square. If it goes down, it's the reciprocal of the square. Because voltage and current are directly proportional. I could put this on a test. I could teach this. And then I could come back and put it on a test and somebody would say 5 volts. So don't feel bad. I expected that. So what would be half power? Well, let's say I drop the voltage down to 70.7%. So I'm going to go down to 7.07 volts. My current's going to go to 7.07 amps, which is going to give me 50 watts. So if I'm measuring power, it's at the 70.7 of the voltage. So I would, if I was going to measure it with my oscilloscope, I'd get me a function generator. I would put it across my media. I'd start at 0 hertz, and I would go up until it builds up on a maximum, right? You understand? And then I'd measure F1. I would start dropping it down so it dropped down to what? 70.7% of the maximum. I'd increase it. I'd keep increasing my frequency until it dropped down to 70.7%, and that would be F2. Now we have formulas to calculate what we expect the bandwidth to be. So this is what I would do. This is why I would use a function generator to calculate the bandwidth of an audio amplifier, because now I can do what? I can start it off at a real low frequency and raise it up and see when the output is maximum, right? You understand? And then do what? Measure it to the medium. And then it should pass all frequencies between that. So that means even if it's doing like this, it would pass it as long as it's within the bandwidth. Now, bandwidth on the internet is how much your internet service providers got all this bandwidth, right? You understand? Are they giving you all their bandwidth? No, they're giving you a what? They're giving you what you pay for. So we got two ways we can put multiple devices on a media. One way is we can put them on there one at a time. So let's say I've got a media that's got 100 megahertz bandwidth. Well, what I can do is I can put a device on there, one device at a time, and it gets all the 100 megahertz. Then what I would do is I would take it off and then let another device. So multiplexing, anybody know what multiplexing is? It's allowing multiple devices to share the same media. Allowing multiple signals. So what I can do is I've got a media that's got 100 megahertz of bandwidth. Well, what I can do is I can let multiple devices share that media, but not at the same time. So one device uses it, then it comes off, another device has access to it, then it comes off, another device has access to it, then it comes off. This is what we refer to as baseband. And this is what Ethernet is. Ethernet is baseband. It uses something called carrier sense, multiple access with collision detection. So what happens is your network device, like my Wi-Fi, if it needs to send data, it looks out there and sees is anybody else trying to send data. If something else is trying to send data, then it'll back off. And what they do is they send information. Everything is split up into what we call packets. So this device would send a packet, and then when it sends its packet, what would it do? It would come off the media, and then it would check to see if anybody else came on it while they was off, right? You understand? If nobody else is on it, then they'd send packets. So right now, am I sending information over this internet on my computer? No. So that means somebody else can do what? Can use it. So all we're doing is swapping. But what's nice is that the person that has it has the total they have the total bandwidth of the media.
Does that website you crashed, Mr. Reed?
No, this is not website. This is Ethernet. This is wired Ethernet. This is Wi-Fi. Wi-Fi uses what we call baseband, which means Wi-Fi, there's only one device on this access point that's sending or receiving information at any one time.
That's why it's so down.
The more people that's on it, the slower it is on baseband. But if nobody's on it, you scream because you got the entire bandwidth. So the less people that's on baseband, the less people on it, the faster it is. This is why when you come in an office at 8 o'clock in the morning and you want to check your email, it's real slow because of baseband. But it's a lot cheaper because the data don't have to be modulated. We can send ones and zeros. The other way we do is we modulate the data. This is called broadband. So broadband would be I come up here and I have 100 megahertz. This is just, I might come up here and I have 10 devices that I can put on there, but each one of them get a bandwidth of 10 megahertz. This is broadband. But what we do is we modulate, the information has to be modulated. So what happens is every device that comes on there uses a different carrier frequency. and then they put it on there, and then it transmits it over there. So this is broadband. So you have a bunch of devices on the network, but no device gets the full bandwidth of the media that they're transmitting. And sooner or later, you're still going to have problems, because if they've got 1,000 megahertz worth of bandwidth and they're giving you 100, right? That's 10 devices. So somebody's still going to have to do what? Wait in line. So you still, even on broadband, it's still up to a point. Once you get so many people out there, right, you'll understand you're still going to have to lose some bandwidth, because why? And they'll do that. They'll vary the bandwidth on you.
So are we saying that baseband and broadband both?
No, broadband, they're both multiplexing, but one of them we call it, in digital, you'll learn it as time domain multiplexing, which means the device does not have to be modulated. We just put the digital data out there. So USB is baseband. So how many devices can you hook up to one USB host? 250 something. So each one of these ports, you could come out to a little USB hub, and you could run all kind of devices off there. So this guy's only got 3 USB ports, and I don't know if y'all notice, every once in a while I put out a little box that's got 5 outputs on it. So I plug it into one. But literally, you can go up to, I think it's 255 devices on each one of your ports. But it's baseband, right? So that's why the more host ports you have, the better it is on USB. But unfortunately, they can't put a ton out here. So this computer's got what? 3, which is pretty standard. So USB is baseband. Yes. But it's still no big deal, because you're not, everybody's not on there. It's still what we call a packet switching network, which means even USB sends information in packets. So it sends a packet and then it releases the line, right? You understand? If nobody's on there, it'll send a what? It'll send another packet. It'll send another packet. It'll send another packet. But after every packet, it does what? It comes off. And the other guy's sitting over here listening to it. And when this guy comes off, it would do what? It would send a packet. So it's kind of like the old party lines that we used to have on our phone system, where, you know, when I was little, we had a party line, and I think there was like 10 people that had our same phone number. But what we do is everybody had a unique ring. I think ours was like 2 longs and a short. But what you would do before you made a call, you'd do what? You'd pick it up and listen, and if nobody was on there, you'd do what? You'd dial your number, or you'd listen to them. You'd cover up the talk and listen. Yeah, you can do everything. So, but still, that was better than calling an operator, and the operator had the big old switchboard up there, and everybody had a plug. Every phone number had a plug, and you'd call up and say, "I want to talk to so and so," and they would take a wire and hook it up on yours and do what? Hook it up on the other one.
They do it as call like some operating system.
That was Mars, though, right? Mars. Wasn't it ham operators?
I don't know.
Did you have to say over every time you got through talking?
No, they transferred the call back to Alabama. There was some place in Virginia we'll call when I was overseas, and they'll transfer a call back to Alabama. I don't know how they did it. I don't think it was a plug system, but it's pretty common.
When we was in, they had it was ham operators. So you'd call a ham operator, and they would make a contact with a ham operator in the United States, and then they would connect that to the phone system. So what you had to do every time you got through talking, you had to say over, because it was what they call half duplex. Half duplex systems mean it's 2-way communication, but it's only one at a time. So I don't know if everybody's dealt with radios, but it's to let you know the other person that they can do what? They can talk. We call that half duplex. Half duplex is when we send information. So we have simplex. Simplex is information in one direction. So that's what broadcast TV is. It's simplex. And then we have what we call half duplex, Now, this is what CB radio is, ham radios. This is half duplex, which means we send it in two directions, but not at the same time. Okay. Which USB is half duplex. Which means transmit and receive at the same, you can't transmit and receive at the same time. Ethernet is full duplex, so you got 4 wires, 2 of them for transmit and 2 of them for receive. So you can do full duplex on Ethernet. So the full duplex means 2 directions at the same time. Now your cell phone does full duplex, but it's really neat. It has a transmit frequency and it has a receive frequency. So that means since they're not running on the same frequency, you can do full duplex. So that's the way these guys work. So you have one frequency for transmit and one frequency for receive. These are full duplex devices. That's why people can keep interrupting you while you're talking, right? But on ham radio, when you're keyed up, the other person can't do what? They can't talk. If they key up, then nobody. So bandwidth is the range of frequencies a media can reliably pass. On internet, though, it's the range of frequencies you're what? You're allocated. So that's broadband. Broadband. If they give you a range of frequencies, then you're what? Then that's broadband. And what's nice about broadband is you can have multiple people on the media at the same time. So that's one of the specifications on your amplifier. When you buy an amplifier, that's what you're going to look at. You're going to look at the bandwidth, right? You understand? The lower the bandwidth, the better you'll hear your bass, right? The higher the bandwidth, then that's where your high frequencies come into play, right? Does that make sense? So if you ever go out and buy a radio, that's one thing, or any stereo equipment or audio equipment, that's what you're looking at. You're looking at your what? Your bandwidth. And then, of course, separation and that kind of stuff. So it's defined a little bit different in this. So what we've been looking at so far is what we call a Class A amplifier. A Class A amplifier would pass 360 degrees of the input signal. No matter what it looks like, it would pass it, right? You understand? It's just that on the output side, you would have gain. And what type of gain are we shooting for? Power gain, right? So we know a common emitter gives us both a power gain and, a voltage gain and a power gain. A voltage gain and a current gain. But the problem is that it's got a fairly moderate input impedance and it's got a really high output impedance. Which means even though we get a power gain, it's not a really big power gain, right? You understand? A common collector doesn't give us a voltage gain, but it gives us a really high current. And then we have a common base, which gives us a voltage gain, but doesn't give us a current gain. So then we get the classes of amplifiers. Then we have Class A. So what's Class A? I just got it out of my mouth, guys. A Class A amplifier passes 360 degrees of the input signal. But it's going to be amplified, right? Y'all understand that? Now, the problem with a Class A amplifier is that it has to be biased on. Y'all understand that? And that bias current is basically lost power. So a Class A amplifier is only about 25% efficient. That's the rule. It could be better, but no worse. So 25% efficient means that 25%, it means that like to get 100 watts out, I would have to put like 175 watts in of power from my power supply to get 100 watts out. So the problem with Class A is they're very inefficient, right? You understand? As far as what power you get out compared to what power you get from your power supply, not your signal. Your amplifier does not create power, it does what? So does amplifiers create power? It manages power. from this guy right here that we call the what? Power supply. So if you get 100 watts out of an amplifier, then by George, your power supply is supplying the what? 100 watts. Plus whatever's required to run the amplifier. So unfortunately, we don't really get anything for nothing, right? You understand that? So what I have up here is I have what we call a Class B amplifier. Now, and we'll see if y'all can figure out what's wrong with this guy.
Class B.
Class B.
B.
What's Class B? No, Class B don't give you 360. If it was if it gave you 360, it would be a Class A. So what Class B gives you, it gives you 180 degrees, so the input signal. 180 degrees of the input signal. But we have a little problem. So this is not quite a Class B. This might be. But notice this is a common emitter. The problem with the common emitter is the input and the output are 180 degrees out of phase. And that's not really a problem, it's just a characteristic. But what you notice, if this was true Class B, this and this would be, so this is turning the amplifier off, this is turning it on, this is turning it off, right? You understand that? So notice what we're getting out. Now this is the problem with this. So I'm gonna come over here and take this, so 1.5 volts. So I'm gonna turn this into millivolts. Okay. And we'll turn the simulation on, and we notice, let me turn my input down really low. Oh, I got 0 over here. So you can see the input is starting to go, but the output is still sitting at 0. And why is that? So here's my output right here. Here's my input. Let's move the output down to the other side.
That's straight line of output?
Yeah, that's the output. So why is the output sitting at 0? I've got an input above the output sitting at 0. Yeah, because I'm only putting what into the base? 2 millivolts. What's required to turn transistor on? About what? About what? What base voltage is normally required to turn a silicon transistor on? It's about 7/10 of a volt. So the problem is my input signal is not turning the thing on. So odds are I'm gonna come up here and so here's 700 millivolts. The simulation looks like it might be. And now what happened? Is the output turned on? If I come over here and put 500 millivolts, then the output turns off. Oh, sorry. I got to increase I'm looking at my input here, so we got to see our input. Let me get that back on. So here's our input. Okay, so it really wasn't turning on. This guy's off a little bit. So here's 700 millivolts. Okay, so the output is still not turned on, right? Here's 800 millivolts. And now the output, now it's turning on a little bit, right? You understand that? Okay. Here's 900 millivolts. And the output's turning on a little more. Here's 1 volt. And here's 1.5 volts. And we can see the output. Now I'll turn the output down a little bit. We're getting a gain out of it. But you can see it's not 180 degrees. And why is it not 180 degrees? Because it took 7/10 of a volt to do what? Turn it on. So what happens is that this is not what we call a true Class B. Because if it was a true Class B, I would be getting 180 degree power. Which means what? It means we're going to have to bias this to Class B. So we can't use this as a Class B amplifier. This is sort of like a Class C. So if a Class A is 360 degrees, a Class B is 180 degrees, what would a Class C be? Less? No. Well, sort of. It would be 90, but technically it's specified as less than 180. So anything less than 180 would be considered a Class C. So this would be probably considered a Class C because it's less than 180. Right? You understand that? Because if it was 180, I would not have that little space right there. Can y'all see that? And I would not have that little gap right there. It's hard to see, but notice, let's see if I can set this at 0. Yeah. And we can't see it, but there's a little space right there because it took what? 0.7 of a volt to do what? Turn it on. So what we'll do is let's bias it a little bit. So what I'm going to do is we'll have to add a second power supply. I think this is going to work, guys. I didn't have time to prove it. And what we'll have to do down here is we'll have to make this power supply the same value. This is going to be a negative supply. So if we had a negative supply and a positive supply, and I didn't have the diode in there, what would be the voltage at the center? 0. So what I've done is I put a diode in here, right? And this is the positive side, this is the negative side, so that should put the base at exactly 0.7 of a volt. Where's my other channel? Oh, we'll probably have to, since we got a bias voltage there, guys, we're going to have to couple this in with a capacitor now. Oh, and I lost one of my channels, sorry. So this should be a Class B amplifier. Hard to see. But what we had to do is we had to do what? Yeah, we had to buy. I don't know if I can invert one of my channels. Let's see. Y'all see an invert on here? Normally on a regular scope, we have the ability to invert the channels. So that way I can put them on top of each other, let you see now they're mirror images of either. The problem we have is that it's what? It's a common emitter and they're 180 degrees out of phase. So this is a Class B. So what's a Class A? 360 degrees of the input. What's a Class B? 180, and a Class C is last thing. Okay. Are y'all following me so far? So Class Bs are okay, but they would be very, very, very distorted, right? Because we've lost what? 1/2 of our waveform, right? So let's pick up something else. So let's come over here and turn this off. And we'll do it this way first, and then we'll come back and bias it so it's going to be a clue. So the one we'll look at now is a Class AB. Yeah. And this is the one you're going to run into in audio equipment. This is the guy that drives your speakers. And what we're going to do is we're going to move to a common emitters. Common collectors. I'm going to take this off. And then down here, what I'm going to do is I'm going to come in here and I'm going to use a PNP transistor. And then I'm going to connect their emitters together. And what we're going to do is we're going to come over here and put a load out here. But this is really cool. So I'm going to come over here and put my load out here. And I don't need a coupling capacitor. So we'll hook the load directly in here. And then what we'll do when we get through, we'll look at some schematics of some actually power amplifiers. Y'all recognize this arrangement right off the bat. So what I'm going to do down on the bottom one, since it's a PNP, is what we usually use it to control a negative power supply, right? And then we'll come up here. This guy is an NPN, so we're going to use it to control positive, but we're going to control it with a positive power supply. And these are both Class B amplifiers. We don't need this coupling capacitor anymore because we don't have any bias on the base. Since we don't have any bias on the base, there's no need to block it, right? We're going to be able to pump this input up. So we got 12 volts up here, 12 volts down here. We got this. So we'll bring in our oscilloscope again. I don't know why I closed it off. Hopefully we can see this. We can use real low frequencies too, and the scope does pretty good on that. So here's our input. Now what's the features of a common collector amplifier? What's the characteristics of a common collector amplifier? Before I turn this on. So what type of gains do we get out of a common collector amplifier? All we get is the current gain because we're taking the output off the emitter, right? You understand? Since we're taking the output off the emitter, the base and the emitter are basically on top of each other, but they're not. And we're going to see, we get a little bit of distortion out of this. So let's come up here and take our input and turn it way up. Can't put, so here's my input. Oops. Oops. Here's my output. We'll try to spread it out and see if it'll still work. I might hook this one up for y'all guys. This is real easy to hook up. This looks okay. So this is a common emitter. Or these are common collectors, right? Taking input on base, outputting on the emitter. So that means the collector has to be common. Here's my input. Here's my output. What do you notice? They're in phase, but what do you notice about the output? Slightly smaller, not much smaller. We can look, we can come over here and put them on top of each other. I didn't want to do that. So we can come over here, and then we can come down here and bring this one down. Yeah, so it's slightly smaller, but it's got that little, we call it crossover distortion. It's got the crossover distortion. Now, why is it slightly lower? Yeah, we got 1.4 volts, right? 7/10 of a volt on top, 7/10 on the volt on the bottom. That's good. But this is what it takes to turn it on right here. Here's the 7/10 of a volt right there that takes to turn it on. So let's move this guy out of the way. So what we do, if we do it like this, we end up with what we call crossover distortion, which means right here where it switches from one side to the other. Can y'all see it, what I'm talking about? Now, if we looked at this on a real amplifier, it would be flat. Right there where it crosses over. So what can we do to do that? Well, we'll come up here and play around with, we'll come up here and we'll bias it. So what I'll do is I'll come up here and bring another amplifier. I'll bring a resistor in. I'll bring another resistor in. Usually this is going to be a pretty good size resistor. So let's just make it 10K. It could be 100K. Just for demonstration purposes. Okay. And then I'm going to rotate them. What I'm going to do is I'm going to take this guy and I'm going to hook it up to my negative supply. I'm going to take this guy, I'm going to hook it up to my positive supply. Okay. And let's move this down some so we got a little room to work with. So what did we do on our other class B to keep it from distorting? I don't know how to do that. I'm trying to move it. So what I'm going to do is I'm going to come up here and I'm going to come to here. And I'm going to take a diode. And I'm going to have to make this bigger. I didn't want to get my transistor. Let's do these two. So what we're going to do is take the circuit that we looked at before, and we'll take this diode, put it like this. And then we'll take another diode. Oops. It's hard to do with the mouse. Then we're going to have to come back and add a coupling capacitor because we got a bias, right? So how is this guy here going to work? Can y'all see what I've done? So here's minus 12 down here, and this looks ugly, but I'm not going to try to rearrange it. This is minus 12 here. This is plus 12 up here. So what would this be sitting at right in the center? So if we come up here and duplicate this, so if I come over here and do this, right, and then if I was to come in here and do this, and then I put minus 12 down here, and I put plus 12 right here, what would we have in the center? It'd be 0 volts. These resistors right here were the same size. Everybody understand that? Yes or no? Some of y'all are looking dismayed. You okay, Joe? They drop the same. So this guy drops 6 volts. This guy drops 12 volts. This guy drops 12 volts, which puts 0 in the center, right? You could calculate the current all you want to, but you'd see that. Well, if these two diodes right here are matched, so here's 0 volts relative to the diode, right? You understand this. Now, this is 0 volts relative to the diode. So what that means is this is 0 volts. This has to be minus 0.7. This right here has to be plus 0.7, which puts the transistors right at what? Right on the verge of doing what? Turning on. They're not really on because we're right at the variable voltage, but they're on the verge of turning on, right? So now the input signal doesn't have to turn them on, right? Y'all understand that? That makes sense? So this is going to straighten out the output a lot. So let me hook my input back up. And then we'll turn on the simulation. And then we'll put them on top of each other. Or try to anyway. And they're going to be in phase with each other. And we've already taken out the 7/10 of a volt for the bias, right? So they should be mirror images. Dang it, sorry. They're right on top of each other. Can't walk. You can't take them apart. Now, what advantage we get out of a common over here? Notice over here I've got 100 ohms over here. I can make these 100K. This is still seen as times beta. This is seen as 100 times 100, right? You understand? It could be 10,000. I could come over here and make these 100K over here. We would have about 500K worth of input impedance compared to out here, right? You understand 100 ohms, right? So we get a ton of current gain out of these things because the voltage input is the same, right? We know the input signal comes in and sees this, so it sees what, but like I said, this would work exactly the same if I came up here and made these 100Ks. Now, why do we call it a class AB? Because it's two Bs generating a class A output, right? You understand that? So if I was to look at the input and I was to look at the output, it would look like a class A amplifier. But this guy here is only conducting during the positive alternation. This guy down here is only conducting during the negative alternation. We put those diodes in there to take out, to make the transistors right on the verge of being what? Turned on. No coupling on this. I mean, we don't need to couple the output because this guy here is putting out this. This guy is only on when it's what? When the input signal goes positive. One transistor's on when the input signal goes positive. One transistor's on when the input signal goes negative, which is pretty neat. The DC that this guy would see would be V peak over pi. I mean, the amount of power this guy right here can handle would be a voltage of V peak over pi. So I mean, we could be getting 100 watts out of this amplifier. These guys right here might be rated at 50 watts. Because they're only on what? 1/2 cycle. This is why we call this a class AB, because even though this is 2B amplifier, by its class B, the output is generating a class A output. This is what you do. This is what we have. This is your every car stereo or every stereo I've ever seen. This is the outputs right here. Class B is 75% efficient. Class A is about what? 25% efficient. So it means to get this guy running, 100 watts output would cost me 125 watts in. So my power supply would have to power this thing up 125 watts to get what, 100 watts out. And class A would be what, 175 watts in to get what, 100 watts out, because it's only 25% efficient. Right, you understand that? So this is the way we go, guys. You'll see these guys all over the place. Some people call them push-pull. These are two class A's, two class what? B's, giving us a class A output. So this is an AB. So we looked at class A's. We looked at class B's. Then we looked at we talked about class C's. Now, class C's are used in really high frequencies. I guarantee you this guy right here is using a class C amplifier to run the antenna. But what we can do is these guys are running at constant frequencies. And what we can do with this is take AC, you'll learn a lot about this. But what I could do is we could come up here and put what we call a tank circuit up here. And then we could come over here and have a class C amplifier. And what happens is, and then if we take our output right here, then what happens is we turn this thing on real hard, and then what happens is your this guy right here called a tank circuit would actually generate this right here, which is pretty neat. We're not going to explain it, but this only works at a certain frequency. So Class C amplifiers, guys, are about over 90% efficient. But we can't use them for audio because audio is all over the place. We can use them for RF because RF, the frequencies are set, right? You understand? And when you set up this tank circuit, we call it a tank circuit, you do it to generate the rest of the signal for you, but it's done with passive devices. And like I said, we're not going to get into the calculations and stuff. And even in AC, we don't get into it, but in AC, you learn a little bit about filters, what we call filters and stuff like that, and characteristics of filters. And so Class C's are about 90% efficient, but they have to run at a precise frequency, right? You understand that? Class B's are 75% efficient, but they can run the entire bandwidth, right? You understand that? And then Class A is about 25% efficient, but we can get all different types of gain out of those. So we okay? Everybody okay? They're different classes. So we looked at all three. You see variations of this guy right here. Let's say we can split them up just a little bit to let you know that they are there. So I can catch them. Huh? Yeah, we're fixing to. And then we'll come back to the left. Are we okay? Of course. All right. Now take a break. 10 minutes, right?